Problem 5 comes from the 2021 AIME I, and it is problem 7. It is a counting problem. Find the number of pairs m, n of positive integers with m and n between 1 and 30 with m less than n, such that there exists a real number x satisfying sine of mx plus sine of nx equals 2. I think the first observation is that the sign has to be between -1 and 1, which means that if the sum of two signs is 2, that means that both of them have to uniquely be 1, right? So when is the sign of something equal to 1? Well, we know that, for example, pi over 2 is an example, and in fact, the set of solutions will just be pi over 2 and then plus or minus some multiple of 2 pi, right? On the unit circle, it would look like all the points whose y-coordinate is 1, which is, of course, just pi over 2. And, you can add 2 pi, for example, to get 5 pi over 2, and so on. Okay, with that out of the way, we know that this is only true if there exists an x such that mx and nx are both pi over 2 mod 2 pi. Note that x can be like any real number. So we can actually make a simplification here where we say, well, we can just scale x by pi over 2, right? So that we just get m times like pi over 2x is n times pi over 2x. And we can see that in this case, this is simply equivalent. We can just divide through this by pi over 2x, or pi over 2, we get mx and nx are both 1 mod 4. Note that it's possible to divide by pi over 2 because we're also dividing the modulus. For example, if we have 8 is 6 mod 2, we can't necessarily say that we can just divide by 2 here. Right? This is not true. However, if we divide everything through, it's basically saying like 8 equals 6 times something plus 2. Divide that whole equation by 2, you will get 4 is equivalent or congruent to 3 modulo 2 over 2, or 1. So we can actually divide through by the whole thing, and we just get this, right? In other words, mx and nx are integers that are 1 modulo 4. Some easy examples of where this happens is where, for example, m equals n. For example, if they're both 1, then we can just let x equals 1, right? If they're 2, we can just let x equals 1/2, and so on, right? It turns out that in order to find such an x, let's figure out when mx and nx are both integers, right? So if m and n are relatively prime, in other words, their GCD is 1, then we can quickly see that if x has any denominator that is not 1, right, in lowest terms, say it's a over b, then multiplying that by m, well, that will only result in an integer if b divides m. In other words, this denominator, right, has to divide m, and similarly it has to divide n, so the only way for x to choose an x such that mx and nx are integers is for x itself to be an integer, right? B has to equal 1. And therefore, right, x is an integer. And since we have mx is congruent to nx, that gives us that in this case, we have a couple cases. For example, if m is even, as just an example, if m is even and n is odd, and their GCD is 1, well then multiplying m by any integer will result in an even number, which is definitely not 1 mod 4. So this situation is not possible, and similarly, if m is odd and n is even, that is not possible. In the case where m and n are both even, they share a common factor of 2, so we'll deal with that separately, right? So let's begin by considering the case where m and n are both odd. So remember that we need this. mx is congruent to nx mod 4, or is 1 mod 4, for some x, right? For example, if m and n are both odd, we can show that they have to be both 1 mod 4 or 3 mod 4, right? Because if one of them's 1 mod 4 and the other one's 3 mod 4, then we can quickly see that x times m minus n, or in this case, right? If we want, so basically we can see that in this case, if mx and nx are both 1 mod 4, first of all, m and n are odd, and so we can multiply by the inverse of m and n because they share no common factor with 4. So we just get that x is congruent to m inverse and n inverse mod 4. And we can see that in order for those two inverses to be the same, m and n also have to be equal, mod 4. So in the case where both numbers are odd, we can very simply write m and n are both 1 mod 4, and the numbers between 1 and 30 that satisfy that are 1, 5, 9, 13, 17, 21, 25, and 29, for a total of 8 choices. And notice that m and n have to satisfy m less than n. So it turns out that any pair of numbers that we choose, we can uniquely assign 1 to m and 1 to n, just m to the smaller one, n to the larger one. So there's a total of 8 numbers, so 8 choose 2 different ways to pick m and n. That gives us 8 times 7 over 2, or 28. Similarly, if we have m and n are 3 mod 4, well, the possible numbers are 3, 7, 11, 15, 19, 23, 27, and there's no larger number there. And there are 7 numbers here, so for 7 choose 2, or 21. Notice that these two cases are mutually exclusive because they're either both 1 or 3 mod 4, but never both. Okay. But what about the case that we didn't talk about yet? In other words, m and n are both even. Well, if m and n are both even, then notice that we can just divide out a 2, right? Because remember that x can be any real number. So if there exists an x such that 2x is, for example, 6x mod 4, or is 1 mod 4, then we know that we can just divide that x by 2, and we can basically use 2x as the new x, and we get basically that this new x satisfies x, so the new x is x prime being 2x, it's just 3x prime, right? So we can see that we can always divide out factors of 2 because x can be any real number, which means that if m and n are even, we divide both by 2 and see what's going on. In this case, right, imagine we had the two numbers like 2 and 8. We can divide this by 2. This simplifies to 1 and 4, and this falls into the category of 1 odd, 1 even. So we know that this cannot be true, right? And in general, if 1 simplifies to odd and 1 simplifies to even, we know that basically no x, right, regardless of it whether it's an integer or not, will produce two numbers that are both 1 modulo 4, right? Because they can't both be odd at the same time, right? This will always have more factors of 2, so therefore it will always be even, provided that this is an integer. All right, so then that tells us that they have to have the same number of factors of 2. So in general, we just have like 2 to the some number, right, k, times some odd number 1, and 2 to the same power of 2 times another odd number. In particular, we need O1 and O2 to follow the same idea here, where they're the same mod 4, right? They're either both 1 or both 3. So then we can just go through all possible values of k and calculate how many possibilities there are for each one. For example, if k equals 1, then the possible values of m and n, well, if k equals 1 and say O1 and O2 are both 1 mod 4, then we can have 2 to the 1 times 1, which gives 2, 2 to the 1 times 5, which gives 10, and then we just multiply basically all the terms up here by 2 until we get a number that's, the maximum, right? Because we need to still stay within the bounds of 1 and 30. So for that case, we have 2, 10, 18, 26. There's 4 choose 2 different ways to pick m and n in this case, right? Similarly, if we have two numbers that are 3 mod 4, well, we just multiply this list by 2. We get 6, 14, 22, and 30 for another 4 choose 2. So that gives 6 cases in each of these. So for the case where k equals 1, right, basically the two numbers share a factor of 2 and exactly 2, and not 4, well, then that means that there are 6 possibilities for the odd numbers being 1 mod 4 and 6 possibilities for the 3 mod 4 for an additional 12 possibilities. Now we can keep going with k equals 2. That will give us this list multiplied by 4 up here. That's just 4 and 20. And then this will be just 12 and 28. So this will give us one additional possibility for this and one possibility for this. So then we finally say, okay, well, if we multiply it by 8, we know that 5 and 7 both exceed 30 when multiplying by 8. So we can say that those are the only possibilities because m and n have to be distinct, right? If we multiplied by any larger number, then we would only have one choice for both m and n, and since they can't be equal, this results in an impossibility. So therefore, we just need to sum up the total possibilities, 28, 21, 6, 6, 1, and 1, and we get a final answer of 63.